Welcome back, everyone. So today, as promised last time, we're going to look at two very specific examples that would give us an insight about how we go about designing the lead and the lag compensator, okay? So I'm going to use two specific examples to go through the methodology that will kind of help you out making the connections and wrapping your head about the concepts, okay? So let's begin with the lead compensator design. Lead design. Okay. So, what is provided to use the open loop transfer function with feedback system like that? G open loop. And what is given to use that G open loop is 4 over S times S plus 2. Now, whether this G open loop only corresponds to the plant itself without any controller ahead of it, or some plant combined with a proportional controller, or some plant combined with a PD controller merged all together in a single transfer function, this is irrelevant for us. But this is our starting point. We have some sort of open loop transfer function provided by this. Okay. So the first thing you want to determine is the current closed loop poles. Where do they stand? Okay. So for that, we're going to look at calculating the closed loop transfer function. And because of this feedback configuration, you should know that this is simply G open loop over G open loop plus 1, which is going to end up to be 4 over S squared plus 2S plus 4. Okay. I can solve that characteristic equation myself, or the prof is going to help me out in an exam and give me that the roots of a polynomial with those coefficients, 1, 2, 4, are going to be S equal minus 1 plus minus square root of 3J. Because the prof is a nice guy, right? So he's not going to let us bang our head against the wall and try to solve a quadratic equation like that on the fly. He's going to help us out to do that. Okay? Yes, I'm a nice guy, by the way, if you didn't know yet. Okay. So based on the location of our closed loop poles in a complex plane, we can determine zeta, omega d, omega n, and based on that, calculate the MP, TS, TP, TR, you name it, right? I'm not going to teach you how to do that today. You should already know based on some previous lectures we did, okay? So zeta for that particular pole location is going to be 0.5. We have an omega n equal to 2 radians per second. Omega d is obviously simply the imaginary part, so that's square root. And based on those three characteristics, zeta, omega n, and omega d, we can determine that our maximum overshoot, which only depends on zeta, by the way, is going to be equal to 16.3%. And our TS, which is 3.9 over zeta omega n, is going to be equal to 4 seconds. Okay, so these are the current closed loop characteristics in terms of transient performance. That's what we have. If you inject a reference signal, you would see the output here stabilizing in 4 seconds and with a maximum overshoot of 16.3%. So that means that if you were to say, I want you to track this step input function, we would stabilize within 2% in 4 seconds, which is relatively short but fast, and the maximum overshoot is going to be 16.3%. Not too bad, not too bad. But is that good enough? That is yet to determine. Okay, at that point, with the closed loop transfer function, with the open loop transfer function, I would highly recommend that you draw the current root locus of the system as it is. Okay? So as it is, imaginary and real axis, we have one pole at the origin and the other pole at -2, like that. And if you were to draw the root locus, you would see this familiar behavior, like this. Okay? Or the arrows denote the motion of the poles as the gain of the open loop increases from 0 to infinity. And now we come back here and say, well, sir, what gain? Well, you have to pretend that there is some sort of k factor that gets introduced by the root locus, and that gain is originally at 0, and thereby giving you the poles of this open loop transfer function. But as this gain increases from 0 to infinity, you're going to get the closed loop pole locations. Okay? This is the meaning of a root locus for a given open loop transfer function that doesn't have a variable in terms of static gain, but has a specific value. Okay? So you always have to pretend that there is some sort of k variable that is going to multiply everything here. Okay. This is what we have in terms of current performance. But the client comes and say, you know what? I'd like a settling time of 2 seconds. Whoa. He better have good actuators. And I'm fine with the current maximum overshoot of 16.3%. All this to say that I need an omega n, which would be equal to 4 radians per second instead of 2 radians per second originally. Okay? And based on the specs provided to you or the requirements, same thing. You have to calculate the desired closed loop pole locations. And by now you should know how to turn specs in terms of pole locations of a complex plane, okay? So the desired pole locations that I shall denote with S star. I'm shooting for the stars, so thereby S star is what I'm shooting for, okay? Going to be -2 plus -2 square root of 3j, like that. So the desired pole locations in red, or S stars, happen to be here and there. Well, currently, if I were to just increase the open loop static gain, if I just take that and multiply it with k, and let k vary between 0 and infinity, I'm going to get this map for the closed loop poles, right? So they'll never go through the desired pole locations indicated in red in this complex plane. Is that a problem? Well, yes. Because currently there's no way that just by increasing static gain will satisfy NASA or the Canadian Space Agency or the European Space Agency or a company who's buying a product from your own company. Okay? So it's okay, I better do something about it before I lose my job. By the way, it's not that drastic, I'm just joking, okay? So you say, okay, this is better than before. So in other words, I need to improve my transient performance, right? That's the idea here. And the prof told me that a good way to do it is by designing a lead compensator. So let's do that. Let's design a lead compensator. But you knew that in the beginning, okay? So pretending that you didn't know which one to pick, this is the thought process you need to go through. Those are my specs I have. Those are the specs I need. And based on those two sets of performance, do I need to improve the transient performance or do I need to improve the steady state performance? And based on that discussion, then you pick the right compensator from your toolbox and design it and then apply it. Okay? So I need to move my root locus further to the left. Or in other words, I'm going to need to bend those branches somehow such that they go through those two desired pole locations. And furthermore, I'm going to come in and design the gain of my compensator such that the poles exactly stop where I want them in the closed loop system. Okay, how do I do that? Well, we need to understand that the lead compensator is actually providing some phase, okay? Because the lead, technically speaking, if you look at some textbook, is going to be referred to as a phase lead compensator. So phase lead implying that this compensator provides additional phase to a system to ensure that the branches go through your desired location. Okay, we need to provide some phase. How does that work? Well, you need to know that the phase of your open loop transfer function evaluated at S equal S star, your desired poles, has to be equal to minus 180 degrees. In other words, this is known as the phase condition. And any poles along a root locus will satisfy this condition. Okay? So evaluating the phase condition when the poles are equal to S star will ensure that the root locus goes through S star. Okay? Because the phase of a pole here is 180 degrees, minus 180, minus 180, minus 180, minus 180 as well here. Okay? So I need to make sure that the root locus then passes through those desired pole locations. And that is done through this phase location, this phase condition. Okay? So this is what I need in terms of end result to make sure that my branches go through S star. So let's see what is my current phase. Okay? Well, the current phase of the system is the current phase of, what do we have? 4 over S times S plus 2, evaluated at the same point, S equal S star. Because if this phase evaluated at that point ends up being minus 180 degrees, the job is over. Because that tells you that the root locus already passes through the desired location. And that's it. We're pretty much done. So let's figure out what we end up when we evaluate the original open loop transfer function that was quantified through these two poles here, one at the origin, the other one at minus 2, but evaluated at S star, which was right above here. What is the phase of those two poles evaluated here? Okay, well, the phase of just a number happens to be 0 degree. So you do the phase of the numerator minus the phase of the denominator. Hopefully you remember how to calculate the phase of a transfer function. And then you figure out the phase of this pole onto S star, i.e. this angle, plus the phase of this other pole onto S star, i.e. this angle. So the phase of the pole directly underneath the desired pole location is going to be obviously pi over 2, or 90 degrees. Yeah. Plus the phase contribution of this pole at the origin onto the desired pole location. So this is square root of 3 in terms of height. This side has a length of 2. So we can figure out that this angle will be, is it square root of 3? 2 times square root of 3. Yeah, I was like, there's something wrong. And so therefore this angle is 60 degrees. Or alternatively, this one here has to be 180 minus 60, and therefore 120 degrees. That is the angle you need to consider. Right? It's always positive counterclockwise. So 90 degrees plus 120 degrees. That is to say that now we are at 210, or that the phase of the current open loop transfer function evaluated at the desired pole locations will be minus 210 degrees. Shoot, that's bad news, because that tells me that currently I'm not going through S star, because if I would have had, then my phase would have been exactly equal to minus 100 degrees. This is the phase condition that tells me that any point along a branch of a root locus will be giving you phase of minus 180 degrees. So again, that just confirms what we already knew, that the current root locus does not go through S star. But now we have quantified that through the phase condition. So we have calculated the current phase of the current open loop transfer function at the desired pole location, and we know that this phase is this, but we needed to have that. So to bridge the gap between where we are and where we need to be in terms of phase is where the phase lead compensator comes from, because the phase lead compensator, just the lead compensator, provides additional phase to ensure that you end up satisfying the phase condition. In that specific example, the phase lead shall contribute 30 degrees of phase, such that currently minus 210 degrees plus the contribution of the phase lead is going to give me what I'm aiming for, and that is my 180 degrees, or in other words, by adding the phase lead compensator in terms of poles and zeros in a complex plane, I'm going to bend the branch exactly to make sure that they go through S star. That's the key idea here, okay? This, did I give it a name? Yeah, I think the phase provided by a phase lead is going to be denoted by phi for no good reasons. But that's what it is, okay? So phi, 30 degrees, provided by the phase lead compensator, or to overcome the fact that we are deficient in phase, right? We are missing 30 degrees to end up satisfying the phase condition. Good, good, good. What now? Well, we know that a phase of a transfer function is the contribution of its zeros and its poles. So if we know that the transfer function quantifying the phase lead compensator ultimately has to give me 30 degrees, that means that the zeros contribution and the poles contribution of my phase lead all together have to provide me 30 degrees of phase, evaluated at S star, obviously. So based on the fact that we know the net contribution, we can design a methodology that will ensure that by placing carefully the zero and the pole of the phase lead, their contribution onto S star will be exactly 30 degrees. There are many methodologies out there or strategies that will allow you to do that graphically or analytically through some equations. The one I was taught as an undergrad student is the one I like the most, and that's the one I'm going to teach you today, okay? So here's how it works. You draw, this is a graphical method, it relies on trigonometry, obviously. So you draw the contribution, or you draw whatever the compensator provides. We know that the lead compensator provides a 0 and a pole, somewhere like that. But we know that the 0 is always to the right and the pole always to the left. But we don't know where exactly yet. Okay? And let's draw somewhere our S star here, desired pole location. S star. All right? This is all arbitrary because I don't know yet where will my pole and 0 of the phase compensator will end up with respect to my S star, but that's not important here. What is important is the methodology. So step 1, the technique to figure out the exact positions of those such that their net phase evaluated with respect to S star gives me 30 degrees is the following. So you draw a parallel line to the real axis that goes through S star. And I'm going to call this line A S star. Okay? And then in the second step, I'm going to draw a line from S star right back to the origin of the complex plane. Next, I am going to measure this angle because I know the exact location in the complex plane of S star, and therefore I'm able to figure out this angle, that angle, and thereby this angle as well. Because this is known. This is at -2 plus 2 square root of 3j. So this side here is 2. This side here, this triangle here is 2 square root of 3. And therefore I can figure out this length, and from simple trigonometry end up knowing this angle. Okay? So the trick next is to cut this angle here in half and draw a line that separates this angle in exactly 2 equal parts. Okay? So I now want this angle exactly the same as this angle, and that was half of this total angle from AS star to the origin like that. Okay? Then I'm going to take my phase contribution. That was our phi angle of 30 degrees. I'm going to cut that in half, 15 degrees. And I'm going to trace lines on both sides of this line that cuts this total angle in half. So one line here on this side and one other line on this other side. And those two lines have to be at phi over 2 from the middle line. Okay, so this angle here is phi over 2, and this angle here is phi over 2. And the intersection of those two lines with the real axis will give me the pole location on the left side of this kind of intersecting line that cuts this angle in half. And the 0 will be the intersection of the rightmost line coming down onto the real axis. Okay? So that altogether, the contribution of this angle and that angle shall be 30 degrees ultimately. Okay? Because a 0 adds angles in terms of phase. Okay? So if you have the phase of the transfer function, you have the numerator over the denominator, and you will hopefully remember that this is the phase of the numerator minus the phase of the denominator. So this 0 ultimately contributes an angle greater than 30 degrees, and this one removes the difference between this contribution and 30 degrees, such that altogether this angle minus that one gives us 30 degrees with respect to the desired pole location here. Okay? That is the idea behind this graphical strategy to figure out the pole and zero location. Now for that specific trigonometry where the desired pole is at -2 plus 2 square root of j, and that we need to provide phi equal 30 degrees, and thereby phi over 2 of 15 degrees, so that is 15 degrees, 15 degrees, you shall end up with a 0 at s equal minus 2.9 and a pole at s equal minus 5.4. I'm going to let you do the work on your own to ensure that you know how to do trigonometry properly and figure, just based on the pole location here, S star, and the fact that you need to provide a 30 angle net phase, how to figure out the position of the pole and the zero, so that you can confirm and put a check mark next to, I know how to design a phase Z compensator. I'm ready to go for the exam, okay? So make sure that you use that as an example and that as a confirmation of the answer you should be obtaining with this zero and this pole location for this specific example again, okay? So now we're pretty much done because we've just figured out the position of the pole and zero of the compensator that we needed to add to the system to provide an additional 30 degree of phase, i.e. to bend the branches so that they go through the desired pole location. But then we haven't figured out the gain of the compensator that will ensure that we stop the poles directly there. Okay? Because we don't want the pole to end short of the desired pole location, nor want the poles to go past the desired pole locations and screw up the transient performance. We want them exactly where we had calculated the desired pole locations, obviously. Okay? But let's just come back to what we have so far. If you look at our new block scheme diagram, we have this. Now we've added a phase Z compensator quantified by K times S plus 2.9 over S plus 5.4. And that compensator will feed the open loop transfer function we had at the beginning. That was 4 over S times S plus 2, if I'm not mistaken. And then we're closing the loop on those two. Bing, bada, bang, off we go. So the last part to figure out is the gain here, to make sure that the closed loop poles stop exactly at S star in the complex plane. Okay. The trick here is to use what's known as the magnitude condition to do that. Because the magnitude condition tells us that if you evaluate a transfer function, 2.9 S plus 5.4 times 4 over S, that's S plus 2. So in our case, evaluating the open loop transfer function, right? Just the multiplication of the compensator with the original open loop. That's what we have. Just want to make it clear that this is the new G open loop that comprises the former open loop plus our new compensator in front of it. If we evaluate that in terms of magnitude, i.e. those two vertical lines, at S equal S star, we should end up exactly with 1. And because the only unknown in that entire equation is K, well, we'll be able to solve that for K equal whatever value, such that when we take the norm of everything with the new K value, we exactly get 1 where evaluated at the desired pole location or the desired bus stop along the new paths. Okay? Nice. But sir, I've forgotten how to calculate the magnitude of the transfer function. Really? That's fine. That's fine. Okay? Because I had anticipated that. So I'm going to show you how to calculate the magnitude of this entire thing evaluated at S equal S star. Okay. So you have to draw the complex plane. Real, imaginary. And you know what? Let me bring the real axis a little bit further down. Like this. Okay. What do we have? We have S star somewhere over here. That somewhere over here is quantified. That's our minus 2 plus 2 times square root of 3. So we know that position. We had the original pole here corresponding to S equals 0. We have the pole at S equal minus 2. So immediately below that. Now we've added an extra pole at minus 5.4. So this is 2, 4, 5.4, somewhere along here. We've added also 1, 0. Where? At 2.9. 2, 3. So this is the compensator, contribution, phase lead. Whereas that was the original G open loop, right? Original G open loop, compensator's contribution. You map out everything you have in the open loop transfer function like that, the new open loop, okay? And now you say, okay, well, the magnitude in terms of this pole evaluated at S equal S star will be simply the distance here. You know this side, 2. You know that side, 2 times square root of 3, and therefore you should be able to obtain that side pretty easily. That one is just the imaginary part of the desired pole, right? Because this one is directly underneath it. So that would be 2 times square root of 3 in terms of distance between this pole and the desired pole location. You do the same for here. You know that this is your 2 times square root of 3. You know that the distance between this 0 and that pole is 0.9, because that one's at minus 2, and this 0 is at minus 2.9, so 0.9, 2 times square root of 3, you can figure out the distance between this 0 and that pole, and similarly to obtain the distance between this pole and the desired pole location in red. Because you have that, you know that this guy is at 5.4 from here, or alternatively 2.5 from this one, and that one was 0.9, so 3.4. That one is 2.4 from this one, so you know this side, 3.4. This is still your 2 times square root of 3, and can then easily figure out the long side of this triangle. Okay, so what you do once you've use your tape measure and measured all these distances, or even better, calculated them using square triangles, right? Because you knew all the bases and you know the height of any of those square triangles. It's going to be the imaginary part of this desired pole, 2 times square root of 3, obviously. What you do is that you come back here and say, okay, I'm going to replace my S in terms of its distance with respect to S star. And that is going to be, which one is which? 1, 2, 3. This one is 4. Okay, the distance between here and here should be approximately 4. Like that. For the S equal minus 2 distance, we know that this is simply 2 times square root of 3. So you see I'm replacing my S minus PI with simply their net distances. The distance associated with this pole location at minus 5.4, if you were to calculate this side, you would get 4.8539. So that's it for the denominator. Okay, 4 stays 4. There's nothing to do about it. It's just a gain, essentially, in terms of the magnitude. And the 0 at minus 2.9 here, the distance between itself and S star, if you do the math properly, you should end up at 3.5791. Okay, so you just multiply this with that and divide this times that. And you'll end up with something here. And all you need to do then is solve for the only unknown, k. So k would be 1 over all of this great thing multiplied together, punched on your calculator. In that case, you should end up with k equal 4.69. And guess what? By cranking the gain of the open loop transfer function, the new one, to exactly this, you will end up with your poles going right through S star and ending up there. So those two would probably do something like that. Boom. Another S star down here, and those two, something like this. I don't know. But what is important is that you've stopped your poles directly at S star by carefully gauging the gain here, and that you've bent the branches to go through S star through the phase condition we saw earlier. So ultimately, you have your compensator's transfer function will be equal to its gain, 4.69. It multiplies S plus 2.9 in terms of zeros. And then what do we have? S plus 5.4 in terms of its pole. So that is your transfer function designed to modify the existing root locus and bend the branches in a particular way to go through S star and end up with your poles at S star. Okay? As simple as that. As long as you understand the whys. So why do we need to provide additional phase here? Well, that was to meet the phase condition. We were deficient in phase. So we needed to provide more phase. 30 degrees. Okay. If my new transfer function needs to provide 30 degrees of additional phase, it means that I need to place my 0 here and my pole over there. Let's do some trigonometry to figure this out. Oh, okay. Got this. And the last part is just to figure out how much gain you need with the magnitude condition, just by measuring the respective distance between each individual poles and zeros you have in the new open loop transfer function with respect to the desired pole location. And that's it. Okay? This is it. So this is how to design a phase lead compensator. And as a result, you have improved your stabilization time and you have made the things more stable because everything was pushed further to the left, which is always good in a complex plane. Okay. Last but not least, let's talk about a lag compensator design. So phase lag or lag design. Okay, why would we need to use that again? Yes, you're correct. That is to improve the steady state performance or the error in steady state. Okay, that is the main point of it. And as I've discussed in previous lecture, the objective here is not to disturb the transient performance because these were good, pretending that they were good enough. So all we need to do here is to improve the steady state, which were kind of bad, by adding a phase lag compensator. If it if we would ended up in a situation where both transient and steady state performance were not good at all, then we would have needed to design a phase lead compensator and then stack on top of it a phase lag compensator, okay? By considering that the open loop transfer function you would begin with the phase lag would be the open loop created by the phase lead combined with the original open loop that we had used to design the phase lead, and use those two together as a starting point for the second compensator in series. But we're not going to go there, but just keep in mind that you can easily stack them together. The design procedure stays the same. What is different is just the starting point in terms of which transfer functions you need to consider. Okay? So here we're starting off with G open loop equal to 1.06 over S times S plus 1 times S plus 2. Open loop transfer function. I'm going to talk about steady state tracking error, ESS. Not ISS, ESS, okay? So let's start discussing about the type of this transfer function. Well, if you look here, we have a pole at S minus 2, another pole at S minus 1, and one pole at the origin. So this is a type 1 transfer function because n, capital N is equal to 1, which implies that we have one pole at the origin, or one integrator, 1 over S, okay? What do we know about that? We know that the steady state tracking error for step input is going to be 0. We know that the steady state tracking error to a ramp is going to be equal to 1 over KSV. Okay. What's next? Well, the next step is to calculate your closed loop transfer function. And assuming that we have our regular feedback architecture, you could say that this is simply G open loop over 1 plus G open loop, or alternatively 1.06 over S times S plus 1, S plus 2, plus 1.06, like this, the closed loop transfer function. All right. But now the poles aren't at 0, minus 1, minus 2 anymore because of this additional term. So the prof, being very kind again, would tell us the roots of such a polynomial equation, okay? So in other words, we will need to solve that by hand. It's not required. So we have two poles that are complex conjugates at minus 0.3307 plus minus 0.5864J. We know that we have another pole, or the prof told us that the other pole was at minus 2.3386, a real pole with no imaginary component. Okay, so based on that, we need to extract ourselves the characteristics in terms of zeta, which would turn up to be 0.491, omega n equal to 0.673, omega d of 0.586 radians per second, which ultimately these could be translated into transient time domain performance, and MP would be about 17%, and TS, settling time, at 2% would be equal to 12 seconds. Furthermore, I can evaluate the current KSV by taking the limit of S towards 0 of S times G open loop, closed loop, and that would give me 1.06 over 2. But wait, we had 3 poles here. So how could you get those kind of things with 3 poles, right? Like omega n is just the norm of a pole. So a real part square plus imaginary part square is square root of, right? This is the imaginary part. So how can you go from 3 poles to one set of characteristics? It's because you need to do the calculations for what's known as the dominant poles. So the dominant ones are the ones closer to the imaginary axis, and those are the ones that will have a greater impact overall in terms of time domain performance it's going to get out of your closed system. That one being kind of further away, and I mean almost 10 times further left of the complex plane, is not the dominant pole. So its influence on the performance and transient won't have a great impact. Right? So those characteristics are only coming from the complex conjugate poles or the complex conjugate dominant poles. Okay? So these are the two. As you can see here, right? Omega d being just the imaginary part directly corresponds to this. All right. So KSV is equal to that. Is that good enough? Let's have a look at the desired specifications. Coming from the client. So desired specs will be same dominant poles. We don't want to move them around, or the client doesn't want to move them around, which tells you that he's satisfied with the transient performance. The transient performance remains unchanged. So MP and TS, which were the ones we calculated, are good enough. 17%, 12 seconds, that's perfect for my application. I don't want you to move them. But you know what? I'd like to have a tighter response in steady state, i.e. I would like to reduce the steady state tracking error. And specifically, I would like to improve steady state performance such that my KSV gives me approximately 5. And we had 1.6 over 2, meaning that we want KSV about 10 times better, okay? And that is the basis of this phase lag design. Looking at the steady state performance we want to obtain compared to the ones we already had. We had KSV of about 0.5, but we want KSV of 5. So we need to improve KSV or increase it by a 10-time factor. Okay? So if you were to look at a current root locus, it would look something like this. Real axis, imaginary. One pole here, another one here, another one here. Those are all the open loop poles. If you look at a closed loop root locus, one pole would fly off to the left. Those 2 poles would meet here and would fly off along asymptotes. Right? Because we have one asymptote here and one throwing everything to the left here. And no root locus in between. Okay, remember the rule of odd and even number. So we have root locus existing between those 2 poles and root locus existing to the left of this further pole located here. Okay, so the poles I had given you from the closed loop transfer functions ended up being somewhere here, there, and over here. And let me draw them in red. And these were, for completeness, the minus 0.33 plus minus 0.5864. Well, let's pretend that they are somewhere over here. And the real pole along the real axis was the minus 2.3386. So somewhere further to the left of this one. Okay? So the red poles are the current closed loop poles without any compensator added inside the system. But because the client said, hey, you know what? Those dominant poles, I really like where they ended up being. Don't touch them. Because I like the way they translate in terms of maximum overshoot and settling time. Or I like their real parts. Because their real parts translate into settling time of 12 seconds, and that is just perfect for me. Don't move them, please. But if you could just improve the steady state performance by a 10-time factor, I'd be over the moon. Literally, okay? You say, okay, what do I have in my toolbox that can improve the steady state performance without touching the transient performance? And you say, I remember. I have this tool here known as the phase lag compensator. Let me pull it out. Let me design it. Let me plug it in my system, and finger crossed, it's going to work out. Okay, no fingers crossed. It's going to work out because I know how to design it. I've listened carefully to all the lectures, and I know I've done the homework, I've done the problem sets, and I'm confident I can design a lag compensator. So let's do it together. Okay, lag compensator in terms of transfer function should look like K multiplies S plus 1 over T. So this relates to the zero location over S plus 1 over beta T, where beta is always larger than 1, meaning that now the pole is going to be closer to the imaginary axis than the zero. This is the opposite situation than we had with the phase lead compensator. Okay? Turns out the factor by which you need to increase your KSV relates to beta. Okay? So I'm going to say that beta that we need shall be equal to 10, because this is the factor by which we need to improve the steady state performance. Okay. So if I have a beta that has to be 10, it means that the zero net needs to be 10 times further to the left than my pole. Oh boy, I thought they were supposed to be almost on top of each other, i.e. not to disturb those great things I already had in place. Because if I were to throw the pole here and the zero over there, I mean, that would completely change the root locus. Because those two objects that have been added through the addition of my lag compensator would just throw everything off, and would have a great impact on the root locus, which was so beautiful to begin with. So the trick to make sure that you ensure a relative position of your zero 10 times further to the left compared to the pole, yet having them close to each other, not disturbing everything, is to really zoom in. You got to zoom here as tight as you can. You got to place the pole as close as you can to the imaginary axis, such that 10 times a tiny bit here would still give you a tiny bit 10 times further to the left. So that first pole that you see here on this scale could be looking like here. And that pole there will be over here. So this is a zoomed in version of this. Okay? Because you want them to be separated, not on top of each other. And that separation ratio is actually your beta, which comes straight from what you need compared to what you had in terms of the steady state tracking error. Okay. So if all I need to ensure is that this ratio in terms of relative position of zero with respect to pole is this, then I'm going to arbitrarily select those two locations. So i.e. I could select the pole location. I'm going to say, let's pick a pole location at, in this example I have here, s equal minus 0.005, almost at the origin, just a tiny bit towards the left. And that's what I ended up picking arbitrarily, yet always close to the imaginary axis. That is the key thing. You have to ensure that the 0 is 10 times further to the left. And therefore, the 0 needs to be at s equal beta times this, so minus 0.05. Okay? That one almost at 0. So the pole almost on the imaginary axis, but the 0 10 times further to the left. And that's why here we don't want to place the pole at s equal minus 2, because that would give you a 0 at minus 20. And now you're going to destroy everything. Okay? And that's not the objective here. You don't want to touch that beautiful root locus that you originally had. All right. Does that mean I'm done? I've already selected my pole to be at 0.005 and my 0 to be at 0.05. Like that. Well, yes, you're almost done. Because here you don't need to worry about the magnitude condition. Because what you need to worry about is the, you don't need to worry about the phase condition, because the phase provided by this pole and the phase provided by the 0 are almost exactly equal to each other. They're so close to each other, right? On the grand scheme of everything, they appear to be on top of each other and at the origin. It's only when you zoom in really close that you see them being separated. So their net contribution to the phase is going to be cancelled by one another, right? The phase of a 0 is a positive phase minus the phase provided by the pole onto the desired pole location, which would be way out there on this scale here. So this angle compared to that angle, this is pretty much the same thing, negligible. So you don't need to worry about that, because the root locus was already going through the desired pole locations. Or in other words, the phase of the root locus evaluated at the pole location was already minus 180 degrees. Maybe by adding that pole and that 0 of the phase lag compensator, you've changed the overall phase to be, I don't know, minus 180.5 degrees instead of minus 180 degrees. But for all practical purposes, this is very negligible, and therefore you assume that the phase provided by those two things are canceled by one another, evaluated at a star, okay? But you need to worry about the magnitude condition. Just to figure out what would be the value of the static gain of your compensator. And you remember the discussion we had in the previous lecture where we said that this gain was almost equal to 1. Well, that is because the relative norm of this with respect to that in terms of distance, real imaginary, between S star and those two things almost on top of each other is going to be almost equal to 1, right? Those two sides will be pretty much of the same length, yet slightly different, and slightly different enough that we consider the magnitude condition to calculate the value of K. But because they're so close to each other, you'll see that this gain will be always close to 1. If you end up with a gain of 5 here, your calculations, you know you've done something totally wrong. So before handing in your design to your senior engineer, make sure that you rechecked everything, because that gain should always be close to 1. Just by virtue of the philosophy of placing the 0 and the pole of your phase lag compensator in the closed loop, in the root locus, okay? So same as before, I'm going to take the norm of our new open loop transfer function, which will be composed of g of c times the former open loop transfer function, and evaluate the norm at s equal s star, and ensuring that everything ends up at 1. This is the magnitude condition that we did. If you do the same thing as before, you're going to say, okay, I've got k times s plus 0.05 over s plus 0.005. This is my compensator transfer function that multiplies the original open loop transfer function, which was go back here, which was my 1.06 over s, that multiplies s plus 1 and s plus 2. Boom. Where or what is the reference for you to calculate the magnitude of everything? Well, that point of reference is s star. And of course, all this needs to be equal to 1 to satisfy the magnitude condition. Okay. Let me just give you the distance of all the individual poles and that single 0 from S star. Okay, so the distance between S star, which is here, or S star is the same as the original closed loop pole locations because we don't want to touch them, and that 0 here, if you do the square triangle thing we did, you're going to end up with a distance of 0.653. The distance between the pole of the compensator almost at the origin of the complex plane and S star, or the original closed loop pole locations, because again they were just fine where they were, it would be 0.674. And as you can see, this ratio here is almost equal to 1 because the 0 is almost on top of the pole, and therefore their distances with respect to S star are almost equal. Okay? The 1.06 remains there. The distance between the origin of the complex plane and S star will be 0.676. The distance between the pole at -1 and S star will be 0.893. And lastly, the distance between the last pole of the original open loop transfer function and the original closed loop pole locations, or S star, is going to be 1. I can't even read my hand writing here. 1.77 maybe, question mark here. I'll let you double check that again to ensure that you know how to design a phase lag compensator on your own, and do that prior to the exam, please. Okay, so the norm of all these things that were evaluated at S star, that gives me a 1 at the end of the day. So as you can see, the only unknown is the gain value K. So you take this, that's going to give you one number. 1 over that number shall give you K, where K should end up being equal to 1.0404. Surprise, surprise. K is almost equal to 1. That makes a lot of sense. That means that by adding this 0 and this pole to the complex plane, you pretty much didn't disturb the original loop locus, because you only need to shift the closed loop pole locations by a tiny bit to re-ensure that they end up where they were before. Okay? That would be 1.0404 will be your compensator transfer function. GC of S. And again, as you could see here, the design of a lag compensator is a lot faster and a lot easier than the lead compensator because you don't need to worry about the phase condition. Okay, so you don't need to do the trick I gave you with the parallel line angle with the origin, cut that angle in half, plus 5/2 minus 5/2 on either side, and do some additional trigonometry to figure out the location of the pole and the location of the zero for the lead compensator. You don't need to do all of that because you had selected, as a good engineer, positions for the zero and position for the pole of the lag compensator intuitively. Yet to maintain the beta factor that was extracted from the desired specifications on the steady state performance. Okay, that was our beta equal to 10 in this specific scenario. Okay, either you trust that you've done a good job and a good design, or what you could do here is to do a quick sanity check on the value of KSV that you would get now with this additional compensator. Okay, so let's do a quick check. KSV, as we saw in previous lectures, the limit of S towards 0 of S times G open loop. Well, our new open loop better include our compensator, otherwise we would simply end up with the previous KSV we had, which was our 1.06 over 2, which wasn't good enough. So S times 1.0404 times S plus the location of the zero you had wisely selected to be 10 times further to the left than the position of the pole you had wisely selected to be very close to the origin, right? Times the original open loop transfer function, 1.06, S plus 1, S plus 2, boom. So that's your new open loop. So now to get KSV, you want to evaluate this whenever S tends to 0. So this S cancels out this one. And you'd be left here with 1 plus 2, or just 2, right? That is the original KSV we had just by looking at our original open loop, if that makes sense. Now, by virtue of adding this, S is equal to 0, S is equal to 0, aha! Now I see where the beta factor comes from. Because the ratio of this over this gives you 10. Right? Because you had ensured beta or 10. You had ensured to locate the position of your pole and 0 to satisfy this ratio of 10. Okay? Such that ultimately KSV be equal to 5.51. which was the objective, to go from 0.5 to 5. We went a bit further than that. That's fine. The client will be happy, your boss will be happy, and you should keep your job for the next decades. Okay.